All right. This is the beginning of the third lesson for our review, course review, third review video. And this end of the last one, we were in the dynamics unit, Newton's laws of motion, and I had gone over, a couple of the common problems. It's the goal of all of these is to review the big ideas, go over the big ideas and the special problem, ways of looking at them, ways of drawing them, ways of drawing free body diagrams, ways of maybe deriving some of the formulas, or just giving some of the formulas. And in light of that, for dynamics, I think, we went over this kind of question, the typical box being pulled at an angle. We're done with that. In the last one, I ended with the Atwood machine, right? With some unbalanced force, due to the fact that they don't weigh the same. It's always given with one's heavier and one's light, right? And usually the question involves drawing free body diagrams, determining what the acceleration of the system is. And, to be quite honest, I remember, and that's why I'm going to bring this up, I remember that the mock exam, which we should look at now, had that as one of the free response questions. So let's see. Sorry, that's not it. This is it here. Nope, not it. I thought I just had it. Mock exam. Oh, sorry. Give me a second here. Maybe it's right behind this. Yeah, mock exam. Right here. So this was your mock exam, multiple choice, free response, right here. And when I go down, this was actually their first question, right? This was the Atwood machine. Looks like my computer's having a hard time loading the full image, not sure why. But this was an image of the Atwood machine with one smaller block on one side and one heavier block on the other side, right? They described it, two cubes connected by a light cord, go over a massless pulley. You're assuming that the mass of the pulley is negligible. And their first question, again, I don't know why the blocks aren't loading. Try again. Let's see. There they are. First question is draw a free body diagram, right? Draw a free body diagram. So, and they want the vectors to be relative to each other in magnitude in terms of their length, right? Any force that you believe is longer or stronger than another force should have a longer vector representing that stronger force. So, let's look at that. So that's what I ended with, but I didn't finish all of it. In the last lesson, I ended with the derivation of the system acceleration. But now let's talk about these parts. So I don't think I did. First, if you just, I guess, fill the screen with the board. If you're looking at, and you draw it a little larger, the Atwood machine, a little larger, and let's just say this was the small one and this was the big one. Then this one weighs more, right? So this one here should have had a shorter vector. I call this little m and call this big M. And I guess we're doing free body diagrams for little m, and we're doing a free body diagram for big M. Then big M would have had more gravity force, more weight, right? Earth's gravitational force would be stronger. I don't remember if they said twice as, to be honest, I should read that more carefully. If they said, one of them was twice as heavy as the other. I don't think they did, but let's just see. Just as the left cube is heavier. Yeah, they didn't say, if they did say that, one of them is twice as heavy as the other, then you would want to be drawing the heavier one with a downward vector twice as long as the other one, because that's representing the relative strengths of the magnitude of their weights. So that's that, right? But these things, even though we know the motion would be down because the heavier one is being pulled with more force than the lighter one is in the downward direction by Earth's gravity, his velocity would be up. We know that the things that are still pulling on them other than Earth below is the rope, right? And you have to know that the tension is equal always in a system on both sides. it has to be that way for internal forces to cancel out overall in terms of the net force on this system. That will not include the tension in the rope. The net force on the system is the difference between the weight of the larger one minus the weight of the smaller one. Big mg minus little mg, right? F net. The net force in the system, again, is big mg minus little mg. It's the difference between them. It's an unbalanced amount, right? This is more downward force than this one. By how much more? By big mg minus little mg. Notice there's no tension in there, right? It has to be that way because even though there's a rope in there in the system, its overall effect on the system as a whole is zero because these are both pointing towards each other. You think of them both as up, but they're not, right? This one's kind of pointing towards the center of the pulley, and this one's also pointing towards the center of the pulley. They're pointing in opposite directions, and it's equal amounts. That's a Newton third law thing, right? One end of the rope pulls on the other end of the rope with a certain force this way. Well, then that other end of the rope must pull on the other end of the rope with the same amount of force, but in the opposite directions. It's Newton's third law, right? So these tension forces should be not only shown equal, but they need to be carefully drawn, right? I can't come over here and just draw a huge upward vector and call it tension. Because if that were true, then for this guy on the right, the heavier guy, there's more upward force on him. He'd be going up, but that's not right. He's going down. He's the heavier one, right? So this one would have to be shorter in magnitude, the upward tension force for him, so that the net force for him is down, right? And then for the other guy who's going to go up, there needs to be. So maybe let me draw his a little longer for this one. That was just arbitrary. There needs to be an equal amount of upward force for him because this represents the tension force. Because again, these have to be equal. These are both equal. But for him, the extra unbalanced amount of force has to be in the downward direction. And it's not to say that they both feel the same net force. No. They have the same acceleration. Right? They will move with the same acceleration. They will gain speed at the same rate. Right? F net equals ma. Right? But if they have the same acceleration because they're locked together by a rope and their motions have to be synced, that's messy. If this is the same value for both, then the one with the larger mass must have the larger net force, right? Because F net is proportional to m, assuming their accelerations are the same. So the larger guy, this guy on the right, he actually has more net force on him than the other one. Just pointing that out. So it's not, if they said draw the net force vectors, you actually would not draw the net force vectors on both of them equal. This guy's here would have to be a little bit longer. And this guy's over here would have to have been a little bit shorter. Yeah. So that's where you would draw the net force. I think the follow-up question after that was derive the acceleration of the system, which we did. Right? We know that the net force is the difference in their weights, and we're just doing the system approach. The acceleration of the system is the net force on the system divided by the total mass of the system. Definitely don't want to forget the net. You definitely don't want to forget the system approach for these kinds of problems. It saves an awful lot of work. Doing it the way sometimes textbook shows takes forever. Just do it this way. Again, the net force, we have it. Mg minus mg. Big mg minus little mg. It's the difference of their weights divided by m1 plus m2. That's easy. As long as you know the process. You factor out g, m minus m over m1 plus, or m, I don't know. I don't have to write m's ones, I guess. I'm just writing big M and little m. So m plus the m. That's it, right? That's the acceleration of the Atwood machine. And they talked about it in the last class, so I'm not going to do that again, but recognize, at least with all the numbers, but recognizing that that acceleration is always going to be less than g. I guess I will. If it was, 5 kilograms and the other guy was 2 kilograms, which I think I did in the other class, then we'd have 5 minus 2 divided by 5 plus 2. 5 minus 2 is 3. 5 plus 2 is 7. So the acceleration will be 3/7 g. That was the example I gave in the last lesson, right? 3/7 of g. It's a less than g for sure. Know that the accelerations will always be less than g. Notice that when the mass of one is much, much smaller than the mass of the other, like an elephant is on one side and a fly is on the other side, then that acceleration of the system should be really, really close to g, right? If I did like 1,000 kilograms was one of them and 1 kilogram was the other, and I followed the same rule over here, m minus m divided by m plus m, m minus m is 999 divided by m plus m is 1001. Well, that's like, 0.999 g or something like that, right? So if one of them is really heavy and the other one's really light, then the acceleration should be just a tiny hair less than g, right? But on the other hand, as their weights get closer and closer together to each other, not equal, because if they're equal, then they won't move. But as their weights approach each other, then that acceleration rate for the system reduces further and further below g, below 1g. And then I think the last question on that mock exam had asked, which one of them will have the greatest acceleration? I believe so. There's the free body diagram. Derive the magnitude of the acceleration, as they always do. They tell you in terms of what they want to see. I just called big M and little m. They call it mass on left, mass on right, whatever. Oh, no. Now, yeah, they could have asked, is their accelerations the same? They both have the same acceleration. But now they asked if the pulley now has a significant amount of weight behind it. It's not like a tiny little made of plastic weight, pulley, but significant inertia to it, rotational inertia we'd be talking about now. And you repeat the same exact experiment. Is the magnitude of the acceleration that you now get, I believe they're asking, is the magnitude of the acceleration of the right cube now greater than, less than, or the same as it was with the massless pulley? Right? They're essentially asking, will the system acceleration, doesn't matter whether it's a right cube or left cube, they always have the same acceleration once they're in motion. So they're essentially just saying, by adding a heavy-duty, solid pulley to this, where its mass and weight is not negligible, would the new acceleration be less, more, or the same as it was before? Well, just think of it in terms of an energy thing, right? As this bigger block falls down, the gravitational potential energy of the bigger block that's going down is turning into motion energy for the whole system, right? Because in this original setup, there's gravitational potential energy for both of them, right? Technically, the little guy's going up, so his potential energy is increasing. But actually, the motion of the system is driven by the loss of gravitational potential energy of the big guy as he goes down, because that's a loss. Potential energy is decreasing means kinetic, that must be transforming into kinetic energy. When the mass of the pulley is negligible, that loss of potential energy for the big guy just gets turned into kinetic energy for both of them as they start to move. However, when there's a pulley involved, some of that potential energy loss due to, again, the big one falling, now doesn't just get turned into kinetic energy for the two blocks. It turns into kinetic energy for the two blocks and the pulley, because the pulley is now rotating. And since its mass is not negligible, its rotational energy is not negligible. It's a big heavy duty thing that, boy, that thing's got some serious rotational kinetic energy, I omega squared, right? 1/2 I omega squared. And so if the pulley is absorbing some of that energy, instead of it being just split up between, not necessarily 50-50 split, but instead of it just being distributed to the two blocks, it's now being distributed to the two blocks and the pulley, then that should slow down their speeds in general, because they're not getting as much kinetic energy as they used to. Some's going to the pulley. So the acceleration would have to be less, right? Acceleration would be less. Or another way of looking at it is there's just more inertia. The system now has both regular inertia, linear inertia for m and m going up and down, but now there's a system that now has rotational inertia, right? And when you add rotational inertia to any system and then say go and allow the same forces to be applied to it, any additional inertia based on Newton's second law, whether it's rotational inertia or just regular old mass inertia, translational inertia, any additional inertia will reduce the acceleration of the system. That's Newton's second law, right? A is inversely proportional to m. But m is really like a m plus I now, if you want to think of it that way. It doesn't really work out like that, but it's conceptually the idea that the inertia is increasing as soon as you have a pulley that has a negligible amount of inertia. And that was it. All right. Not necessarily going to the mock exam by any means right now. But figured why not mention that one? Since it was related to this one that we were talking about. All right, let me get another page. Boom. All right, now we're moving on to, I don't know, we could do one like this. These show up also. Special problems. We'll call this one M1. We'll call this one M2. And we'll say there's no friction. Now they could, you could reference free body diagrams, right? This guy now has some tension. This is static, by the way. We're going to say it's just in static equilibrium. That was my intention, was to talk about this problem when it's in static equilibrium. It doesn't have to be. If mg sine theta, pulling this thing down, is significant enough, this will definitely move in that direction. It won't be static equilibrium. Mg sine theta is still pulling down, right? This guy has some tension over here pulling up. He has some weight pulling down. Those would have to be balanced in a free body diagram, because if it's static equilibrium, that means the net force on him has to be 0. And for the other guy, the tension would have to be the same as the tension for the first guy on the left, same length, right? And mg sine theta, which is pulling him down, which we usually would just call FGX, would have to also be equal to FT for him, because some of the forces on him along that x-axis, remember, which goes this way, should be canceling. Does he have a normal force being applied to him? Yeah. But there's also a FGY force. So those along the y-axis are canceling, and the forces along the x-axis are canceling, right? It has to be. Static equilibrium means any part of the system that you look at, if it's not moving, the net force has to be 0. All forces in one direction have to be equal to all the forces in the opposite direction in all cases, no matter which directions you choose. If it's up, then the ones that are down and up have to balance. If it's up and to the right, then the ones that are up and to the right have to equal the ones that are down to the left. Or, if they ask, what is the tension? What is the tension in this? I mean, we could return to just point out, I gave a similar problem in the last lesson. What's the tension? Same question over here now. Static equilibrium. You might remember that the tension was, well, it would have to be mg sine theta. In this problem, right? The tension pulling up, Ft, would have to be equal to mg sine theta. What about now? Based on this right here. The tension in the upward direction must be equal to mg sine theta, because that block doesn't care who's holding him up. This block here that's sitting on the ramp, he doesn't care if it's a wall with a rope attached to a wall, or if it's not the wall that the rope attaches to, but the rope actually runs over a pulley and attaches to an object that now uses its own downward weight to prevent the guy on the ramp from falling. The guy on the ramp doesn't care. He doesn't even know, of course, not even a person. All he knows about is forces. He doesn't even know. He does feel, he does experience those forces, and he moves or doesn't move based on balanced or unbalanced forces on him, right? So you could have picked either one to express this, just pointing that out. Had you looked at this guy over here, you would have said that the tension is equal to little m times g. It must be. Looking at the other guy, you would say that the tension must be equal to mg sine theta. I guess I'm calling him M2 and this guy M1. Is that what I did? Yeah. Right? It has to be. If they asked, what is the angle of the ramp? They can do that. That can be sometimes the question. Well, based on everything I'm showing here, we technically have two expressions for Ft, 1 and 2. And we know that the force on both sides of this rope have to be equal. This tension up on him and the tension over here on him, those have to be the same, because it's Newton's third law. So that means the tension we've written here has to be the same as the tension written here, which means those two things should be equal to each other. And that also makes sense, since if you just looked at the endpoints and ignored the rope, the force that's on the right side of the system, mg sine theta, has to be equal to the force that's on the other side, all the way on the other side, which is this little guy hanging here. The force pulling him down is little mg. Right? Little mg must be equal to mg, I don't know why I'm saying little mg, just m1g times m2g sine theta. Right here, right? That must be true. Solve for the angle of the ramp. G and G cancel, right? Sorry, I'm just getting a little messy, so clean it up. So we ended up with m1g equals m2g sine theta, g. So we end up with sine theta equals m1 over m2, which tells us the angle should be equal to the inverse sine of m1 over m2. So whatever the ratio of m1 over m2 is, if you do the inverse sine of that ratio, you should get the ramp. This is the ramp angle. What if all of a sudden the guy on the left was a little lighter? That could have been the problem. They don't give a static equilibrium problem this time. They decide to say that there's going to be motion. That this guy that's on the right, that this guy that's on the left, he's going to start moving in the upward direction. And the reason we know that is because they just tell us. They say the guy that's hanging over here, M1, after the system is released, begins to move up. And then for this guy that's, I don't need all of that stuff anymore. For this guy that's over here, he begins to move down the ramp. And the reason we know that is because they just tell us. They outright say it, no problem. He begins to move down the ramp. Determine the acceleration of the system. Well, again, just look at the endpoints. The internal rope forces cancel, not of interest, other than knowing that they're equal in an opposite direction on each of the blocks. We know one side we have mg sine theta. Yanking it down this way, I'll call that m2. And then on the other side, we have pulling in the opposite direction of mg sine theta is m1g. Those are fighting against each other, those two forces, right? If they said that it's moving down the ramp, then we know m2g sine theta must be greater than m1g. It must be the greater force. There must be a net force in this direction, if that's the direction that everything moves, right? So if we want to know the acceleration of the system, what do? We divide the net force on the system divided by the total mass of the system. So we have mg sine theta. Messy, sorry. We have m2g sine theta pulling down the ramp minus m1g on the other side, all divided by m1 plus m2. Again, I mean, some of these you'll remember. I wouldn't expect you to memorize all these. No, but I mean, I think seeing these each of the processes again before an exam, because you could get some of these on the free response. Yeah, you're like, oh yeah, I do remember that. Just saw 4 days ago. You're not going to memorize all these boxed formulas. Some of them you will. Right, so that will be the acceleration of the system. I mean, they gave you numbers, gave you the ramp angle, gave you M1 and M2, gave you G. Pointing out, you would put in a positive, well, not 9.8. They want you to use 10. You would plug in a positive 10 there. You don't plug in another negative there, because you already took care of the negative of G right there. Negative M1 times G. That's negative because of G being down. So you don't plug in another negative and you'd undo it. Just point that out. All right, so there's that, and it's this problem, very common problem in static equilibrium scenario, in motion scenario. All right, move on to I'll just hit the next page. Now let's look at, let me come over to my list over here and check that one off. These are, by the way, usually called the modified Atwood. That one we just looked at was modified Atwoods. Because that's where I started with regular Atwood. Regular Atwood, boom, 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 like this. And then as soon as we start doing things like this, these are all modified Atwoods. The next one we're going to do is now the one that you did the lab earlier in the year. Very common. This one is very common. Call this one N1, call this N1, 2. What if there's no friction? They didn't talk about friction in the last one because they usually would not talk about friction on that one that we were just, this one here. It wouldn't usually reference friction. But it is worth pointing out, if they did, I could see them maybe having one question at the end saying, there was some tension in the rope when it was set up like this with no friction, the way we talked about it. And there was some amount of tension in the rope when it was all just in static equilibrium. Everything was just sitting there. In another trial, we set up the same exact system with the same ramp, but this time there's friction. There's static friction involved, the frictional surface. Same weights, same angle, same everything. The only thing that's different is there's a little bit of friction in there now underneath this guy. What happens to the tension force as a result of this new addition of friction to the system? Does the tension in the rope increase? Does the tension in the rope decrease? Does the tension in the rope stay the same now that there's some friction in there? Well, if he has some force pulling down, which was mg sine theta, right? And before there was friction, it had to be, Ft had to be the same amount in the opposite direction. Made that a little too long. Ft would have had to been, this would have been Ft, right? This is originally what we're thinking. Now we have, if he's sitting on this ramp, static friction is actually acting on him up the ramp, right? The static friction force, the impending motion is in this way. It's the way he wants to go. So that means the static friction force is this way. So if we add another force in this direction, in this direction now to my original picture, what would have to happen to the tension force so that the tension force plus the static friction force is still as long as this one? Well, it looks like the tension force would have to decrease, right? This would have to now get a little shorter because he has somebody else on his team helping out. Friction is now on his team helping out. So the tension force would decrease so that this one plus this one now comes out as mg sine theta. Right? Having a little extra friction on there takes off some of the load from the tension in the rope because the static friction force is doing the same thing as the rope is trying to prevent this thing from falling down the ramp. That may be mentioned. I don't know. Usually not. Usually when they give those, and they do, they don't reference. But on this one, they do. We'll start with no friction. Free body diagrams. Fn, right? M1G. With the other guy. M2. Oh, forgot. Sorry. There's some tension here. And then for this guy, same amount of tension. Remember, they both feel the same amount of tension. And let's assume that they've described this system that's going to move. When it's all set up, the system begins to move. Here it is, and this is what it looks like. When it's all set up, it begins to accelerate. We know that this guy, if that's true, is not going to go the other way. It has to, friction can't pull it across the table to the left. It would have to be motion in this direction. Right? What would be the acceleration of the system? After the free body diagrams, again, then these tension forces are not of interest. They just kind of communicate the motion to each other, but they don't drive the motion of the system. You're just looking at the two ends, right? This force down is M2G. How much force is pulling this way? None. There's none force. There's no force pulling this way, right? Look at it. Look at his free body diagram. The normal force up and his weight down, not of interest. They cancel. The tension is to the right on him, right? So you're looking at the two ends, which I always recommend, the two far two ends of the system, which I did here. And now I did over here and realized that there's none because there's no friction in this problem. Then the net force is just this, not that one, this one here, M2G. Yeah. If they say in another problem, but now in the next problem, there is some friction on the table, which is what they do. Once there's some friction added to the table, the system is set up, and again, it begins to move. What will happen to the acceleration of the system once there's some friction along the tabletop under here? and derive a new formula for the acceleration of the system. If that were the case, we would show it in the new diagram here, that there's some kinetic friction, sliding friction force to the left. It has to be less than the rightward force. Why? Because he's moving to the right. They've described the same setup with some friction, but he still moves to the right. The other guy still falls down. That means the net force on this guy over here must still be to the right, which means this tension force must be greater than this frictional force, right? Not equal. It would have to be longer. Right? So if I added that to this diagram here, I'd say, all right, because that's what I recommend as you think through these problems. What's the net force? Again, just look at the two endpoints. The two ends of the system have two things pulling in this case. M2G, which is still there, check. But now he's fighting against the opposite direction force, which is FFK. How would we re-express the frictional force on him? It would be mu K times M1G. We're just adding that. And it's a net minus, right? Because the new acceleration can't be as great as it was on the frictionless surface. As soon as some friction is involved, that's a resisting force. It's almost like adding inertia to the system. That acceleration is going to decrease. Adding mass or rotational inertia to a system, it's going to decrease the acceleration. Or in this case, add some resisting force like air resistance or friction. What's going to happen to the new acceleration? Always going to be less. Right? Always. And that's why this is a minus. It has to be what we had before, minus the friction force, still divided by M1 plus M2. Moving on. Check. We will then now talk about, just point out quickly, just so you're aware, sometimes they draw, these ones, and I want you to know that there's not much that different. They try to fool you sometimes by just presenting them differently. One like this. This one's big and heavy, and this one's light, and they say that they set it up, and this guy, he goes down. Same sort of questions as usual, draw the free body diagrams, what's the acceleration? It doesn't matter. It doesn't matter. Or they do this one. Here's a block like this, connected by a rope, and another block, and there's a force pulling it to the right called F. And we'll call this one M1, and we'll call this M1, M2. Free body diagrams. Fn. Fg, I guess what I call it 1. Fn. Fg2. Some force F. What is the acceleration of the system? It's a system problem. You have to recognize these are system problems. 2 blocks, there's a rope. Doesn't matter what it looks like. Is there a ramp? Is there a block like this one, or a table like this one, or it's on the floor? Doesn't matter. Acceleration of the system is always the net force on the system divided by the total mass of the system. You just have to check the 2 endpoints. This force is pulling to the right, assuming there was no friction. Along here, who's pulling to the left? None. There's no force pulling to the left. You might think that's his inertia or something. Well, we already take care of the inertia of him, right, in this denominator, right? His inertia will have to reduce the acceleration. We can't think that his inertia is going to go into F net. Although I could see why you would think that, but I'm just telling you, you can't. There is no force going to the left. There's just a force to the right. So it's F divided by M1 plus M2. That's it. Once there's some friction involved on this problem, now there's friction on here. All right, well, then we would have to add that to our diagrams. There's some sliding friction force. I don't know who's greater. It would depend on who's heavier. If the M2 is heavier, then there would be more friction force on him. If he was twice as heavy, there would be twice as much friction force on him because the frictional force is proportional to weight. Mu mg. Mg is weight, right? Frictional force is proportional to weight. If this was the case again, all we have to do is subtract, because now we can't cross out this backwards force. You have to, no, there is some. Or let me point out one other thing that you could do. You could just say, heck with the rope. Imagine this being one block with a mass of M1 plus M2. You can do this. It's being pulled by a F force F to the left, to the right. There's a frictional force back. Just knowing that when you do the frictional force, it's going to have to be in reference to M1 plus M2. And that's it. Let's do the problem, right? So what would the net force be? F net, I don't know why that doesn't look like an alpha. F net is equal to F minus mu times the normal force, right? But we would usually put mg there, but we're actually going to put m1 plus m2 g, right? Because now the total normal force in the upward direction is, again, dependent on the total weight down, m1 plus m2, it's supposed to be 2, I'm not sure why I did that, g, right? Total weight, so the sum of their masses times g. Yeah? So that means the normal force up, even though I drew it small, it's really the same length as this one, but up. And that would be the normal force, and that would go here. All divided by m1 plus m2. If I divide it by f1 plus m2, then which I did, this is now the acceleration of the system. Who accelerates with a greater rate? Neither of them. They accelerate at the same rate. Same thing on this other one. This tabletop one. So I'm not going to do it all, but same ideas. You know, when they did this a few years ago on their free response question, because they do release their free response questions every year. After asking a question about the setup that we see right here for this one. This one's what I'm talking about. Then in the end, they say, oh, well, what if we were to go like this and now add a mass there like this? Big one. No friction. There was no friction ever mentioned in this one. What would happen to the acceleration of the system, assuming that the system still goes down, let's say, just as before? But now we added a big mass in there. There's no friction, not a frictionless surface above. What happens to the new acceleration? Oh, you're adding inertia, and acceleration is going to decrease. That's Newton's second law, right? Moving on. Let me go over to my little list over here. Check, check, check. Let's look at the hanging sign. I think I'm good with all of these ropes and pulley stuff for now. At least be done with that. Let's look at the hanging sign. Here's our hanging sign. Usually they provide the angles measured from the rope. These are both ropes here. The ropes. Usually they measure the angles from the rope to the vertical. Call that theta 1, call that theta 2. Usually. I will point out if they're the same angle, because that could be a simple or simpler one. If they are the exact same angle, these are just made at the same angle, theta 1 and theta 2, and these are, equal. That's Q. I don't know why I did Q. Theta 1 equals theta 2. So if they're equal like that, remember that the downward weight of the sign is absorbed by the tensions, upward tension component in these two ropes. So if they're equal, if it's symmetry because they have the same angle, and let's just say just conceptually that mg came out as 100 newtons, let's just say, then this one would have to be 50 newtons, and this one would have to be 50 newtons. Because the total upward force, 50 plus 50 from the two ropes, would have to be equal to 100, because that's how you get static equilibrium. As soon as the angle changes, then it's not a 50-50 split anymore. It's not I don't mean 50 Newton split, just a 50% split of the load, which would be the weight. As soon as you have some breakage of the symmetry of the rope angles, then things change. So if we looked at this one, this would be considered his FT component. This, I'll put Y. I should have put Y on these, I guess. Y components. And this rope is now pulling to the left with the force of FTX. This guy's force is pulling rightward, FTX. And this one's pulling up, FTY. I don't know why I have two FTYs there. Just need one. First idea, concept, the FTXs have to be equal. I didn't draw it that way, But whatever this guy's x component is for this tension, it must be equal to this guy's FTX. Because those are the only horizontal forces at play here, right? If we free body diagram it, we would show that the weight is pulling down, mg. We've got some tension. I didn't draw that quite right. The way I had it was a little more steep than that. We have some tension kind of pulling it up like this. I guess we call that F2, if we call that rope 2. And we have another tension going this way. We would call that F1. The bottom line is when you, and they don't want components in your free body diagrams. They want just the vectors like I've drawn here. And in fact, this one would end up being a bit shorter. We talk about why that is in a minute. We're trying to say the x components would cancel out, I think is all I was saying. And their y components, these y components would collectively add up, still collectively. So I guess that's what I was trying to point out. If this was, his y component, the upward direction, ft2y, I guess is what we would do, ft1y. It's still the same idea that ft1y plus ft2y still equals mg, right? So the amount of force in the upward direction from one of the ropes, the left side rope, plus the amount of upward force in the y component from the right side rope, ft2y, still has to be equal to the total downward mg, right? So if this was, I don't know, if it was the 100, like I said before, let's just say if this was 100 newtons, and now this guy's was, I don't know, let's just say 80 newtons, I'm just totally making that up, then this guy's would be 20 newtons, right? The one that's more vertical absorbs more of the weight, something for you to know. The one that's more vertical absorbs more of the object's weight. The closer and closer this right rope gets to the vertical, the more and more of the weight it absorbs. That's the reason the tension in the rope on the right is always greater. Because if you're comparing two ropes again, one that's like this and one that goes up like this, we already know that their x component tensions have to be the same because it's not moving right or left. It's the only, that's what I was saying before, I forgot. It's the only leftward force, it's only sideways forces involved, right? Gravity is down. Each rope has a y component up and two left components, one to the right, one to the left. So those definitely are balancing. So they're the same. So when you're comparing both ropes' tension, if they have different magnitudes of their tensions, if FT1 and FT2 are different, which they are, I'm telling you, FT2 is more, it can't be because of FTX. Those have to be equal, since if it's 10 newtons to the left, then it must be 10 newtons to the right, right? I'm just making up the number 10. It doesn't matter what the number is. Just whatever the amount of leftward forces for one of them is the same amount to the right. Because the guy that's more vertical absorbs more of his weight, and I'm trying to tell you that, because I'm not going to go into all the math of this, because usually it doesn't come into play, like the guy did on the College Board thing. It's not worth it. Usually, I mean, I could maybe do a simple derivation, but I'm not going to go through all the complicated stuff. Usually the questions relating to the sign problem are the concepts that I'm telling you right now. The idea that the upward force component of one plus the upward force component of the other is equal to the total downward force, because that's a static equilibrium idea. All upward forces have to equal all downward forces. All rightward forces have to equal all leftward forces. It's a static equilibrium idea. And again, that the tension in the guys that's a little more steep in his rope, F2, will be stronger tension, more magnitude, because he's absorbing more of the load, because he's more able to. He's got an angled rope that's more vertical, so it's able to absorb the downward vertical gravity force, right? If you have a rope that's going this way, attached to a block that was hanging, let's just say by some other one going up in the air, how much of the block's weight or load can this sideways rope absorb? How much weight can a rope pulling straight to the left, how much of this thing's weight, if it was hanging again, because there's another rope going this, how much of the block's weight can the left one provide? How much of the block's weight can the left one absorb is what I meant to say. It's zero, right? Leftward things can't absorb downward things. This X and Y axis. We talked about this, independence of motion, right? If this were the case, like I'm talking about here, They actually have one which they do sometimes, attached to a wall, it's attached to a wall. Then this guy's y component is the only upward force, which must be equal to mg. Right? Then his upward component has to fully be equal to mg. And then this guy's rightward component must be equal to however much he has to the left. But his tension, FTX, is not absorbing any of mg. All of the blocks or sine or whatever it is, weight is absorbed by this one. And as soon as that rope, again, gets more and more vertical, it absorbs more and more of the weight. Lastly, I'd comment just, if you had to actually model, the actual tension, just remember it's just all vectors, right? FTX, FTY. Be aware that they usually report the rope, which is going this way, the angle from the rope to the vertical. And if you decide to draw a triangle like I just did, and if they said, for example, that this angle shown in the diagram is 30 degrees, and this would have to be 60 degrees, right? 60 plus 30 has to be equal to 90, the complementary angles. Be aware of that. This is an easy spot to make a mistake if you were actually being asked to model it with some formula. I'm just pointing out, how would you, magnitude of the tension squared equals FTX squared plus FTY squared. It's Pythagorean's theorem, right? Or if you knew FTY, maybe you found out, like in the problem I had above, that this guy, this one here, that his FTY is absorbing all of his weight because the other rope is straight to the left. Maybe you found that out. And they've given you some other information about the rope on the left. Maybe they told you that the other guy's leftward tension was the rope pulling to the left. I'm talking about now a problem where there's one rope pulling straight to the left and another rope straight up. And they tell you that this is 100 newtons. What is the tension in the other rope? Well, just conceptually, right? If his leftward force is 100 newtons, then this rightward force must be 100 newtons. Because 100 newtons to the right and 100 newtons to the left have to cancel. It's static equilibrium, right? And as soon as I know that, and I know that this rope was the only upward component rope that had an ability to absorb some of his weight, then I could do mg out. They tell me the mass was 10 kilograms. 10 kilograms sine. Then his weight would have been 100 newtons. That means I now know that from a triangle standpoint, this is 100, this is 100. How would I get this? Pythagorean theorem, right? Put in 100 and 100 for the two sides and square root, right? Just square root, cross this out. All right, I'm not talking about the sign anymore. Done with the sign. Now let's go over to the elevator. Another common problem. An elevator has some. It almost always has some. Well, let's not do the boxes. In fact, I think it's going to be my last problem for now. Take a break. There's a man standing on a scale in an elevator. Very common. The elevator is accelerating in the upwards direction at a rate of let's just say 3 meters per second squared. And the man's mass is 100 kilograms. What is his apparent weight? You need to know this language. What is his apparent weight? When they say his apparent weight, and that's exactly the word they use, apparent means that it appears to be a certain weight, but it's not his real weight. When this elevator is just standing still and not moving, then, for me, I looked around and I see about 200 pounds on my scale. But the moment that this elevator starts accelerating upwards, if I'm in the elevator on the same scale, accelerating faster and faster and faster, whoa, I feel this elevator accelerating me up. I'd feel a little extra pressure in my knees. They would tighten up a little bit because there's more upward force from underneath me. And if I look down at my scale, because I'm still standing on the scale as this elevator just goes faster and faster in the upward direction, and I look down, I might actually see it says 212 pounds. Soon as the elevator actually goes to become a constant speed, reaches some maximum speed, and now continues in the upward direction at a constant speed, I look back down and I see 200 pounds again. Because if I'm going at a constant speed, then the forces on me must be balanced. My weight mg down must be balanced with the normal force up. The normal force is what the scale reads. You need to know that. When they ask about what the scale reads in these kinds of problems, Fn, what we always talk about is Fn. It's the pressure underneath you. That is what the scale reads. If you're standing on a scale, the scale reads whatever the normal force is, the weight underneath between you and the scale. That's the normal force. Right? So as soon as I'm going at a constant speed, like I was talking about, then if I'm going at a constant speed, I know my acceleration is 0. If I'm going at a constant speed in the upward direction. And if I'm going at a constant speed in the upward direction, not accelerating, that means the net force on me must be 0, which means the normal force and my weight must be equal. For me, if it was in pounds, 200 pounds, right? But when I am accelerating, if I am accelerating, there means there must be a net upward force. Back to my original one, if he is accelerating, that means there needs to be more upward force on my body as I'm in this elevator than there is downward force, which is just my weight, right? And now the normal force must get longer. This normal force must get longer while accelerating so that now there's an extra amount of force in the upward direction. And if there's an extra amount of force in any direction, we call that the unbalanced or net force. There must be an acceleration due to it, right? How would we model this? Fn is up, right? No funny things with the signs here. Fn is up, minus mg, that's down, divided by m. That would be the acceleration if they asked you to just derive a formula for the acceleration of the system. Or they don't, and they actually give you the acceleration of the elevator, and you can stick it in right here. And they give you the mass of the man, check, check. And they, you know G is 10. Then what's the only unknown? The apparent weight. That is sometimes the question. Essentially what they're saying is if he looks down at his scale while accelerating upward in this elevator at 3 meters per second squared, what is his apparent weight? What does his weight appear to him as when he looks at it? It's not his real weight again. It would be more, right? Then you would just have to do some algebra to solve for Fn. Right? I guess A plus, just multiply both sides by m. You get m times a back over here, right? Equals Fn minus mg. And then you would just move over your mg to the other side. Technically, if you factored out your m, you'd end up with m a plus g, where you would be putting in 10 here, and you'd be putting in 3 here. That's how you would do that. You wouldn't want to put a negative in there. You want a bigger number now, right, than 10. Because now it's 13 times his mass. That means that's a lot more force than just 10 times his mass, which is his weight, mg, right? That's how you would do that. Know that the normal force is what the scale reads. What if he was going downwards? If he's going downwards, will the scale read more than what he weighs, still what he weighs, or less than what he weighs? If he's, I should have been more specific, accelerating in the downward direction in an elevator. It's going down and it's gaining speed as it goes down. I do have a phone call, but it's not super important, which is not, I'm not going to answer it. What if he's going down? This will be the last one. He's going down, he's accelerating. He's gaining speed as he goes down. There he is, sitting in his elevator. Draw a free body diagram for the man. Normal force would have to be the same, longer, or shorter than mg. If he's accelerating down, A, B, or C. If he's accelerating downwards, that means there must be a net force downwards. That means there needs to be extra force downwards, right? That means you need more downward force than than upward force, which means it would have to be C, right? There have to be, if this is what he weighs, just as a reference again, this is his weight vector in the upward direction, just mirroring it in the downward direction. Then the normal force, the scale, must be less than what he weighs. Because if it's accelerating down, then there has to be extra force in the downward direction. Right? That makes sense. Opposite is true when he was going up. If he was going up, there needs to be extra force in the upwards direction because he's accelerating up, and then the normal force would have had to have been more than what he weighs. Yeah? And you would have done the same way. If they ask, well, what is what is his, I don't know, acceleration, or you just use Newton's law. F net equals ma. If it's this scenario here that I was talking about, you would still say Fn is up. Even though he's accelerating downwards, the scale is still pushing up on him. Minus mg, because his weight is down, equals ma, right? And if this was the case, you could actually just solve, if they just outright ask you for Fn, then you just, boom, you go right to it. Fn equals ma. Oh yeah, so we have to be careful here. So this is one of those ones where A is actually down. Remember, we said that, so before it didn't matter because it was just automatically plus. A value is automatically plus if you don't do anything to it. In this case, if we say that in my problem I'm talking about now, where he's accelerating in the downward direction, which is negative, I would actually have to come over to this spot here where I have ma and stick in a negative a. Because that means his acceleration is down. Before it was plus, I didn't have to talk about it or mention it because it was already up. He was accelerating up. Right? So when we do that, we get, just cross this out, just looking at this, if we solved for Fn, we'd end up with Fn equals mg, because when this minus mg comes over to the right, it'd be plus mg minus ma. This is go accelerating up. What was it before when he was accelerating down? Mg plus ma, accelerating down. The normal force, again, is what the scale reads. They're not going to say, though, what the scale reads. Wish they did. It makes more sense. They'll say apparent weight. Quite literally, you'd feel lighter on your feet. There'd be less pressure underneath your feet, between your feet and the scale, if the thing was in a free fall. Not in a free fall, but accelerating straight. Free fall means just truly free fall, just accelerating around down at G. Which, by the way, let's point out, what would the normal force be if the rope got cut? If you're accelerating downward, right? If the rope gets cut, we know that what is your acceleration going to be if the rope gets cut? Assuming there's no air resistance again. There would be on the bottom of the elevator, pushing up. No air resistance. What would your acceleration be if the rope gets cut or breaks? You're going to accelerate at G, going to be a free fall. What would the normal force be? You would come over here and plug in right here. The acceleration would actually be negative G, right? Because the direction of your acceleration is down at a rate of G. And you'd plug in again, negative G. What is that? That's negative mg. What's this one? Plus mg. What's mg minus mg? 0. Aha! That tells us that the normal force would actually be 0, which tells us what will the scale read while you're plummeting down this elevator. Elevator, I don't remember the name of it. Those long tunnels. What would the scale read? Free fall. It says 0. Fn would be 0. That means your feet would come up off the scale just a little bit. Not a lot. You would fly up and smash your head into the top, but you would kind of float slightly above the scale. And if someone could look at that area between the scale and your feet, they'd see they're separated. What do you apparently weigh? What's your apparent weight? 0. Are you really weightless? Einstein tackled that one. The difference between an acceleration and a gravity field is very gray, and that led him to his theory of relativity. But certainly you feel weightless. Certainly feel weightless. because you don't feel your weight in your muscles. You're just in free fall. All right. One more comment, I think. I'm stopping. The one more comment is about the same problem, just a little different. They put boxes in the elevator. It comes up a lot. It's very common. A big box, and there's a little box, and it's a small box, and they call it box 1, box 2, box 3. And then the same idea. This thing is accelerating upward. What is the normal force under block 3? What is the normal force under block 3, for example? Just think of it as one giant block that has a mass of 1 plus 2 plus 3. What would the weight be under here? I didn't mean to say that. What would the normal force be under here? It returns to the man. This is now a man that has a mass of m1 plus m plus 2 plus m3. It's accelerating up, and the same problem. Don't be fooled by the blocks. Or they say, while the elevator accelerates upward with these boxes, the way it's shown in the diagram, we're now interested in what is the normal force acting on block 2, right here. How much is acting on him? Well, if that's the case, then we're now grabbing these 2 blocks and saying they have a mass of m1 plus m2. And there must be some force pushing them up. Where is that force coming from? From block 3, pushing up on block 3. Which way are they pushing on block 3? Down. Which way is block 3 pushing on them? Up. Well, technically, block 3 is only pushing on block 2 up, and block 2 pushes on block 3 down. It's Newton's third law. You would repeat the question if they asked for the normal force in the elevator that is accelerating upward at a rate of a. Just noting that the normal force can't be as much as it was before. There has to be the most pressure under here because all of their weight is crushing down on that spot. And here, there must be less normal force because it's just the weight of 1 and 2 pressing down on the spot. You would repeat the same calculation the same way, like I said, but you'll get less of a normal force. And there would be less normal force under here because that's just now dealing with his weight. All right. I think I'm going to end there. I actually covered a lot of my pictures that I have over here. I did my elevator, did my sign, I did all the other ones. In the next lesson, we're going to move over to circular motion. I've got centripetal on the agenda for that lesson, centripetal force, centripetal acceleration, in general, the ideas. Then some application problems, special problems. The rotary in the car, static frictional force for a car that goes around a rotary. You did that lab, pivot lab. The spinning bucket that's spinning like this. We talk about the tension in the rope at the top, at the bottom, or what's the minimum speed that the bucket has to have so that water doesn't spill out at the top. Remember all those. Maybe you don't remember all the details. That's why we're reviewing it, but you probably remember talking about them. After the spinning bucket, we're going to talk about gravitation, Newtonian's law of gravitation, right? The force between planets or stars, GMM over r squared. Surface gravity, the gravitational acceleration due to gravity, G, on the surface of a planet. Or out later, we talk about what would G be far, for due to Earth's gravity. We know G is around 10 here on surface where we live, but what would Earth's gravity acceleration be, G, out some distance out there? Because even if you put something far, far in outer space and let go of it, it still starts moving towards Earth. Way out in outer space, it feels Earth's pull and moves towards us. Does it accelerate at G? 10? No. Accelerates at less than 10 because Earth's gravity force is less out there. So you weigh less out there. Right? And that pull towards Earth is less. And if the pull towards Earth is less, then the acceleration has to be less. So we get to that part too. And we have surface, like I said, surface gravity or G out in other places in space, outside of a planet or star. Orbital velocity. When we start to equate mv squared over r, which is the centripetal force formula, equal to the gravity force, gmm over r squared. We did a lot with that back then. It's very common to have to equate Newtonian's gravitation formula, gmm over r squared, equal to mv squared over r for the thing that's going around the orbit. And you can work out all sorts of things and solve all sorts of problems by just setting those two things equal. We come to that. Then we have the centripetal force and acceleration that we talked about in the beginning as it relates to planets and orbital motion. Then we talk about escape speed, which I realized I missed. I never taught you about escape speed. The speed that a rocket needs to be moving at in order to literally escape a planet's gravity and never come back. Because there's always some limited amount of fuel on a rocket. And yeah, you can take off and go super, super fast. You eventually will run out of fuel. At some point, you'll start just kind of coasting away from Earth. Earth's gravity is still out there. It's really weak, but it's still out there. It's a small force back towards Earth. Since the rocket would still be going away from Earth, but still feel a little bit of force back towards Earth, it would be slowing down. Any force in the opposite direction of motion will slow you down. And that would continue happening, right? Keep happening. And eventually, if you're slowing down, even if it's a little bit each hour, at some point, what's going to happen to your rocket? It's going to stop. And then that gravity force is still there. It's a little bit, but it's still pulling on you with Earth gravity. Then what happens? You reverse direction and you start falling back towards Earth. So you might wonder, oh, we can't leave Earth. We can get really far away from Earth, but there's no way of getting away from Earth. Eventually it'll stop us and eventually pull us back, just like it does to apples and basketballs when you throw them up in the air. Turns out the answer is that's not correct. There is a very fast speed needed called the escape speed for all gravity fields, like the Earth's gravity or Mars, and you need more speed to get away from bigger, heavier planets, and less speed to get away from smaller planets. But it's called escape speed. I didn't teach you about it. And you can solve for what that speed of your rocket needs to be so that once it goes away, it will never come back to Earth. It'll continue coasting further and further away from Earth forever and ever and ever and never return. It won't have a trajectory that eventually stops it and brings it back. Escape speed. We'll get to that. And then we talk about energy, about orbits, about potential energy between planets. Perhaps they are either just fixed at some distance or orbiting around each other. And then we talk about kinetic energy while in orbit. And then we end with Kepler's law. Kepler's laws, I should say, there's 3 of them, right? And that, from what I can tell, is my plan for the next lesson, which will actually finish Newton's laws. It'll finish it off. Then when I get into the next lesson, it will be energy, more than likely one lesson, and then one more lesson for momentum. I don't know if I'm going to be able to make one for rotation. We did just recently do rotation, so it might be reasonable for me just to say I'm done at that point. But we'll see. If I have time and energy left in me, I might make another one for rotation. But again, it's pretty fresh. It's something we just finished. If I had to do just 3, it would have been kinematics, dynamics, and then energy and momentum. So at the minimum, again, we've got one more lesson coming for all the things I just listed, one more lesson for energy, one more lesson for momentum. And then we're done. And then we will be heading into the AP exam with confidence, calmness, and certainty that we will do the best we can do. That ends it for now. Ends it for now. I'll be seeing you soon. Bye-bye.